Okay, in this podcast we are going to look at the mole and molar mass and how we use these concepts to start doing calculations in chemistry. It's a good idea to have a periodic table handy. I'll refer back to that often, and your Unit 5 packet with the notes for moles and molar mass. So if you don't have those, hit pause and go get those, and then return, and we will continue with the podcast. Okay, the first thing we want to do is define exactly what the mole is. And this is a very simple concept, yet it still gets misunderstood amongst students. So I just want to emphasize that the mole is simply a number. If I had said to you 1 dozen is equal to what, you would all simply answer 1 dozen is equal to 12. So if I said you've got 2 dozen eggs, you would know that you have 24 eggs. The mole works under the same concept. A mole is simply this value. So the official definition is 1 mole is the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of the carbon-12 isotope. So take 12 grams of carbon-12, count how many carbon atoms are present, and that number is going to be 6.02 times 10 to the 23rd. So it's important to realize that when we're doing these conversions and we're talking about moles, we're talking about groupings of that number. The same way that when we talk about dozen, we're talking about groupings of 12. 2 moles, or 2 dozen is 2 times 12. 2 moles is 2 times 6.02 times 10 to the 23rd. On a side note, if you're not familiar with scientific notation yet and comfortable with it, you need to get there in a hurry. So please see me in class if that's an issue. Alright, so let's do some simple conversions using this concept of the mole. So we're going to say 1,450 apples is equal to how many moles? So we'll start with our 1,450 apples. And what I want to do is convert that to moles. So I'm going to put my conversion factor, and then I'm going to put apples, and then moles of apples. So we can say 1 mole, we get the 1 from there, is equal to or equivalent to 6.02 times 10 to the 23rd apples. So again, as we did before with dimensional analysis, when you do the math there, it would be 1,450 divided by 6.02 times 10 to the 23rd, and that's going to give us 2.4 times 10 to the negative 21st moles. The important part about dimensional analysis is that at this point is that the numbers that we're going to be using are either very large or very small. So the dimensional analysis helps make sure you get the right answer when that intuition isn't there. In other words, it's pretty hard to determine if 10 to the negative 21st is a realistic answer. That's why you have to trust the dimensional analysis. Alright, let's take a look at the next problem. It says how many moles of water are there in 3.4 times 10 to the 12th molecules? So let's start. We've got 3.4 times 10 to the 12th molecules of water. My pen is writing a little funny right now. And we are going to convert that to molecules. So we're going to put 6.02 times 10 to the 23rd molecules in the denominator, and we're going to put 1 mole of water in the numerator. So when we do the math there, we're going to get 3.4 times 10 to the 12th divided by 6.02 times 10 to the 23rd, and that's going to give you 5.6 times 10 to the negative 12th moles. Again, the dimensional analysis is going to help ensure that the math is correct when the intuition won't tell you if that number is correct or not. Let's do another conversion here. 1 mole. If 1 mole of carbon has a mass of 12 grams, how many grams of carbon are there in 3.2 moles? So we'll start with our 3.2 moles of carbon. So we draw our conversion factor. We have moles of carbon in the denominator, and we're looking for grams, and our conversion says that there are 12 grams of carbon in 1 mole. So we're simply going to go 3.2 times 12, which gives us 38.4 grams of carbon. Alright, so now that we have an idea of what moles are, let's move on and do some calculations where we involve some chemistry. It says, how many atoms are there in 5.5 moles of dinitrogen trioxide? So we start with our 5.5 moles of dinitrogen trioxide. So right away you're going to see that you've got to know how to name and write formulas, otherwise you're going to have a pretty serious problem. So we'll set up our first conversion. We're going to say 1 mole of dinitrogen trioxide contains how many atoms? So we know that there's 6.02 times 10 times 10 to the 23rd. Now dinitrogen trioxide is a molecule, so we're going to say molecules of dinitrogen trioxide. But we're looking for atoms, so what we need to do is one more conversion, and we're going to say 1 molecule of dinitrogen trioxide contains 5 atoms, 2 nitrogens, 3 oxygens. So we'll put our 5 atoms in the numerator. That way moles cancels with moles, molecules cancels with molecules, and what we're going to be left with is atoms. So when we do the math here, 5.5 times 6.02 times 10 to the 23rd times 5, we're going to get, let's see, where can I put this? 1.65 times 10 to the 25th total atoms. And that should make sense, since we started with 5.5 moles. There's a whole lot of molecules in 1 mole, and then there's a whole lot of atoms in those molecules. Alright, let's move on. Next question says, what's the mass of 4.5 times 10 to the 23rd or 10 to the 30th atoms of magnesium? Again, start with the given, so we'll start with 4.5 times 10 to the 30th atoms of magnesium, and we'll start our conversions. So we're going to put atoms of magnesium in the denominator, and the only thing we can go from atoms to is moles. So we're going to say there are 6.02 times 10 to the 23rd atoms of magnesium in a mole of magnesium. But we want grams, and it says here that there's 24 grams for every mole, so one more conversion, we can say 1 mole of magnesium is equivalent to 24 grams. So again, atoms will cancel, moles will cancel, and we're going to be left with grams. So do the math. 4.5 times 10 to the 30th divided by 6.02 times 10 to the 23rd times 24 is going to give us, 1.8 times 10 to the 1, 2, 3, 4, 5, 6, 7, 10 to the 8th grams. Now that's an awful lot of grams, but if you look, that's an awful lot of atoms, so that should make sense. Okay, what we're going to do now is talk about molar mass, because we want to apply this concept to different compounds from the periodic table, and to do that we need this concept here of molar mass. Now we explained this in class, and I'll just go over it quickly here. When you look at the periodic table, what you're looking at is the mass number, and that's the larger number for each element in the periodic table. So for example, carbon has 2 values on the periodic table, 12.011 and 6. Remember, the lower number represents the atomic number, the larger number represents the atomic, or represents the average atomic mass. But what we're going to say now is that that is the number of grams per mole of carbon. So for example, if you had 1 mole of carbon, that would be 6.02 times 10 to the 23rd atoms of carbon. If you put that on a balance, it would weigh 12.011 grams. So what that means is if you look at, say, for instance, magnesium on the periodic table, its mass number is 24.30. The units for that are grams per mole. In other words, there's 24.3 grams of magnesium per mole of magnesium. That's going to allow us to convert between grams and moles. So when we're trying to calculate our molar masses of compounds, what you've got to do is add up all the molar masses of that compound. So for example, water is H2O. So to find its molar mass, you've got hydrogen and oxygen present in the compound. You've got 2 hydrogens and 1 oxygen. So look up the molar masses on the periodic table and you'll find that the molar mass for hydrogen is 1 and the molar mass for oxygen is 16. 2 times 1 is 2. 1 times 16 is 16. If you add those together, you get 18. And again, remember, the unit is grams per mole. So we can say that the molar mass of water is 18 grams per mole. If we look at carbon dioxide, add up its molar masses from the periodic table, you get 12 plus 2 times 16. So we have 1 carbon, molar mass of 12, 2 oxygens, each with a molar mass of 16. That equals 12. That equals 32. Add them together, and the molar mass of carbon dioxide is 40. That's a 4. 44 grams per mole. Carbonic acid, H2CO3. So add them up. 2 times 1 plus 12 plus 3 times 16, you should get 62 grams per mole. Nitric acid is HNO3. So we have 1 plus 14 plus 3 times 16, and we get 63 grams per mole. Phosphoric acid is H3PO4. So we have 3 times 1 plus phosphorus is 31, so plus 31 plus 4 times 16 gives us 98 grams per mole. Ammonium sulfate, NH4, 2SO4. Now this one, the compounds that we have present here are nitrogen, hydrogen, sulfur, and oxygen. But look, we've got parentheses around the polyatomic with a subscript of 2.